Today I want to talk to you about the formula booklet. This will be about the AA formula booklet, but some of the formulas are the same, and also a lot of the comments that I'm going to make are going to be really generic and not about any formulas in particular. So first of all, there is this question about whether I think it's good to have a formula booklet or not, or if it would have been important for students to memorize all these things. And I want to make it very clear, it is good to have a formula booklet, okay? I don't think memorization is helpful. Myself, I don't personally even have the times table memorized all that well. What I do have are mental strategies that I can use to come to the answers when I need something like 6 times 8.
Ah.
And that is the same for a lot of the formulas in the booklet. I don't necessarily know them by heart as symbols in a line, but I do have knowledge in my mind that helps me come up with the formulas. But if you tell the students that you're not going to have a booklet, that you're going to have to necessarily come up with the formulas from your mind, that is very stressful, and that very understandably puts a focus in the students' minds of having to memorize. I think memorization is going to come very naturally for a lot of things, just like with repeated use of the formulas and also by knowing where they came from. But the pressure of knowing that you have to memorize shifts the focus to a very weird place, which is memorization without understanding. That is the worst of all worlds when it comes to formulas. So yes, it is a very good thing that we have a formula booklet because the students then don't have to do that. I still think they will end up memorizing a lot of the stuff in here. And I do take issue with some of the formulas in the booklet specifically. So this thing here about arithmetic sequences is a very good example of the kind of thing that I am talking about. The nth term of an arithmetic sequence, because formulas are important, they have a very important role in math, but they are not what math is. Math is understanding the concepts. And the concept of an arithmetic sequence is that you start from a single term, and then for every term that you move along, you're adding always this number d, the common difference. So plus d plus d plus d plus d. That naturally leads to this. So this doesn't need to be a formula. This is just knowing the concept of an arithmetic sequence. And although it can be helpful to have that formula sitting there in the booklet, because you also have the one for the geometric sequence. So if you have both of them there, I don't know, this can be helpful in case you forget the names, right? Which one is the arithmetic and which one is the geometric again? So you go to the booklet, you will find both of these things, and then you remember the arithmetic is the one that adds and the geometric is the one that multiplies. But if you are planning on relying on that formula for arithmetic term in order to solve the questions, sometimes you're going to make it more difficult than it's supposed to be, because it is a formula involving 4 variables like this. And if the problem is giving you 3 of them and asking you to find the 4th one, that's perfect. Something like this example, which gives you 3 of the 4 variables and asks you to find the 4th one, which in this case is d. But not all questions about this formula are like this. In fact, a very common type of arithmetic sequence exercise gives you just 2 random terms, like 3 and 8 here, without giving you the first one, and then they ask you to find u1 and d. And if you want to solve that kind of exercise by blindly following the formula, of course you can, but then you have to apply the formula twice and do a bunch more calculations later. It has become a system of 2 equations and 2 unknowns, and then you solve it in the usual way that you do. And I know that this kind of thing, a page with a lot of lines looking like very mathy math, this can look pretty. Yeah, I think it kind of looks pretty, but it can also look ugly and sort of scary. And that's a problem, I think. If you look at a question that was as simple as this one, and you think that it will require this much math to solve it, then you are pretty much correct to be scared. Because the correct way to solve this problem is to just know what an arithmetic sequence is. Then you can either draw something like this or just imagine it in your head. But the point is that from 5 to 8, you're moving 3 terms, And in those three terms, you increased the number by 9. So of course, D is 3, which means that you can also fill in the rest of the blanks, and U1 was 5. These two strategies are actually the exact same thing, okay? So the 3D equals 9, so D equals 3 thing that I just commented here, it's written here, the two lines that I'm marking with the green arrows. So this is the thing that it's important to understand about formulas. They are not there to make your life scary and difficult. They are there to represent what you think about the concepts. And they can be important, not in this exercise. Those were small numbers. You didn't need a formula for that. But of course, if it was a lot more, then I would have, if not blindly used the formula from the booklet, but at least not draw a picture. And the interesting thing to notice here as well is that U8 was U5 plus 3D. We've mentioned this a couple of times. So if this is going to translate to a formula, it's not going to be the one that's in the booklet. It's going to be this one, which is a more general version of the one that is there. So this is the thing. Somebody made choices about what is in the booklet, what is not in the booklet, and we can have opinions about choices. The thing below it, on the other hand, in my opinion, is an example of a very good formula, because the sum of the terms of an arithmetic sequence is nowhere near as obvious as finding out what a specific term is. I do have a video that I will link in the description explaining how to get that formula for the sum of the arithmetic sequences. But in the classroom, I don't even always do that, because I know that not all the students are interested in knowing where the formulas came from. And this is one that even if you do know where it came from, if you watch that video, if you understand why the sum of the terms of an arithmetic sequence has to be given by this formula, in practice, when you're solving a question, you're not going to do that. You're just going to apply a formula that you have either memorized through repeated use, or you're looking it up in the booklet. So this is a perfect formula. I'm happy that it's there. Not to say that only easy topics have irrelevant formulas in the booklet. Here is complex numbers. And the complex numbers section of the formula booklet, of course only in the high level booklet, starts with saying that a complex number is z equals a plus bi. So I don't think any student is looking that particular formula in the booklet. If you've studied complex numbers, you know that you have a real part and an imaginary part, and that you can write that as a plus bi. But what a lot of people do forget, and is not in the booklet, is what is the complex conjugate of a number. So that would be a minus bi, and that's not in the booklet for some reason. And I really think it should be, because it is something that people forget, unlike this one. Okay, so that was sort of an introduction. I haven't really started counting down my top 5 least favorite formulas. And I am sure that when you read the title of the video, there is a strong possibility that you felt that this one would have been one of my least favorites, the infamous quadratic formula. That's not the case, actually. I very much like teaching the quadratic formula. I also like teaching students to look for faster ways in some situations, like when it can be factored. It's easier to factor. When it can complete the square kind of easily, then you should do that. But the thing is that in the general case, when the numbers are not wanting to help you, when they're not like x squared plus 5x plus 6, then the quadratic formula is your best bet. It is the thing that's going to work every single time. And although the deduction of the quadratic formula is basically just completing squares, so like it's within the reach of all the students, I also have a video doing that one. But it's not something that is fun to do, especially not doing it over and over again, like every single time you need it. So I would actually put the quadratic formula at the other end of the list. It's one of my favorite formulas to teach, because it is very helpful. It works every time that you try to use it. It's not something that you want to waste time deducing again when you need it. And it is not obvious the format to memorize, so it should be in the booklet. So this is a perfect formula. Another extremely good example of the exact same thing is the cosine rule. Students in this course do have the tools necessary to deduce the sine rule and the cosine rule, but it's not something that in practice anybody does. We don't deduce it over and over again every time we need it. We just know it by heart. But memorizing intentionally is always a bad idea for learning. So yes, this should definitely be here in the booklet. I'm happy that it is. I have a little bit of an issue of it being written twice, like once with the c squared being the subject of the equation and another with the cosine of c being the subject. Because come on, this is just algebraic manipulation. You can isolate any term in that first sentence, and you should be able to do that. Isolating variables in an equation, not something that I feel a student should have to look up in the formula booklet, but that is my only issue with this formula. So I recorded this video a couple of months ago and then I forgot to post it, so I'm coming back to it. But since then, I think I may have changed my mind about that last point there about the two versions of the cosine rule being in the formula booklet, both of them, because I recorded another video about the demonstration of the cosine rule, which I will also link in the description here. And among other things I mentioned there that I think it's okay to have both. So, well, I think I'm ready to tell you now what some of my least favorite formulas to teach are. And here are two of them at the same time. At number 5 and number 4, you have these things. The distance between 2 points. This one is in three-dimensional space, but the 2D version is also in the booklet. This is Pythagoras. This is not a separate formula. I find it a little bit weird that Pythagoras is not in the booklets, not even as prior learning, because come on, we love Pythagoras. Everybody loves it. I know that there is a little conversation that needs to happen to convince the students that the three-dimensional version also works. And this conversation does need to happen in class where you draw a little cuboid and do Pythagoras on the base and then another Pythagoras going vertically to then conclude that, look, there is an analogy to Pythagoras in 3 dimensions as well. This is good because for some reason that I don't really know, Pythagoras is a formula that most students are pretty okay with. They don't see it as a difficult thing, so why not use that instead of trying to tell them that distance between 2 points is another thing that they might find difficult. If you want to find the distance between these 2 points, why not just tell your students to put them inside of a right triangle? Triangle gains a third point here that you can find its coordinates because you hope your students know how the coordinate plane works, right? So they should be able to find the coordinates of this point. But if they can't, that's a very good opportunity to talk to them about the coordinate plane again. Now you have the perfect situation for Pythagoras. From 5 to 1 is 4 units. 5 units in the horizontal between 2 and 7, and then you just use Pythagoras to find your hypotenuse. This does not make the exercise take longer at all. If the student was doing this with the stupid formula from the booklet instead, he would still have one line before the first one that I wrote, which was to figure out what x2, x1, y2, y1 are, not make a mistake in any of those 4 numbers, and write the formula here, and then all of the other steps would be the same. It doesn't take longer to draw the triangle than to do that. And the other stupid formula that is right next to it is about the midpoint. Again, this one is the three-dimensional version, but the two-dimensional version is also there. And I'm going to use the same drawing to show you why this is stupid. There's the midpoint in the middle. You just want to find his horizontal and vertical coordinates. Well, the number that is directly in the middle between 1 and 5 is 3. And this is the way that I like my students to get to the 3. I don't like 1 plus 5 is 6 divided by 2 is 3. To do the same in the horizontal is going to take a tiny little bit more work because 5 is odd, but you can still find the point that is exactly in the middle between 2 and 7. So there you go, your coordinates for the midpoint. This one's actually easier to convince the students that it works in 3 dimensions as well. Easier than the distance formula, which actually requires some work. I used numbers the whole time, and the students are going to be working with numbers in their problems too, so why not? You have 2 formulas right next to each other. One of them has x1 minus x2 and the other one has x1 plus x2. You don't think that the students are going to mix them up like half the time? Is because those 2 things are very similar. But that only happens if they are trying to apply the formulas without understanding the content behind them, which is exactly what I'm trying to avoid. That is the reason why these two are on the list of my least favorite formulas, as is this one as well. Let's make this number 3 on the list. The slope of a line is rise over run. I'm sure your students know this. But this formula is horrible. It has 4 different variables. It has minus signs that are going to generate some confusion as well, especially when you have negative numbers, because then it's going to be minus minus, and that confuses a lot of students. But they know that it's rise over run, so why not get them to really quickly sketch something like this and see the rise and the run? So the rise is 4 because we went from 1 to 5, and the run is going to be 5 going from 2 to 7. So slope is rise over run, in this case 4 over 5. Very quick, no confusion with 4 variables in a formula, no wasting time looking for the formula in the booklet. But I was looking through the formulas that I set out to show you, and I realized that I didn't have 2 more for the list. So let's go back and make this one about the term of the arithmetic sequence as number 2 on the list. Okay, my second least favorite formula to teach for the reasons that I've already mentioned. Okay, so the next one, the very first formula on the list of things that I don't like to teach, is actually going to be the one where I am most willing to be convinced otherwise. Okay, so I'm going to explain my reasoning. And if you disagree with me, please try to convince me in ways that will make sense to me, not just saying that formulas are good and should be used all the time, because that will not convince me. And this here is what I am talking about. Standardized normal variables, very first formula on the top of the list of things that I don't like. So this is not a particularly complicated formula, as you can see, but that's not the reason that makes me like or dislike formulas, is not how complicated they look. It's what kind of knowledge they are hiding from the student, knowledge that I would like them to have, and that I don't think they will have if they rely on the formula, because they will bypass the knowledge. So this formula usually appears in a very specific type of exercise, which is something like this. You have a normal distribution x, and there is at least one of the parameters is unknown. I'm doing an example where we know the mean is 5, but we don't know the standard deviation. And then there is some other information that we have about the variable. In this example, I'm putting that the probability of it being bigger than 7 is going to be 0.2. And the way that I tell my students to handle this kind of problem, which is a very common type of problem in the exam, is to draw it like this, side by side with another normal distribution, where I tell them to pick the normal 0, 1. It's easy to convince the students that any normal distribution would work, but that the normal 0, 1 just makes for easier calculations. And then I don't know why I use the letter K for that. That would be Z. That would be what the formula considers Z. So let me just change the letter here. Okay, so the important knowledge that I think that formula is hiding, which this method displays, is the fact that every normal distribution looks exactly the same. They can be stretched out if their standard deviation gets bigger, and they can move side to side if their mean is different. But other than that, they look exactly the same, in the sense that the amount of standard deviations that you have to move to the side of the mean in order to get a particular percentage left over is always the same. So if this was going to be like 0.5 standard deviations to get 0.2 probability here, then this would also be 0.5 standard deviations in order to get 0.2 probability here. Of course, exactly how much to the right of the mean we would be by going 0.5 standard deviations depends on what the standard deviation is. But that is exactly what we want to find in our problem, so that is useful. Okay, so I was saying 0.5 off the top of my head just as an example, but then we use the inverse normal in the calculator to find the actual number, which is this one. I'm not going to show you how to do that in this video because that's not the point, but if you want me to, just let me know and I'll do it another day. Maybe I did already do it in a video where I talked about the normal and binomial distributions. I'll link that below here and you can see if this is there. But the point is, the important knowledge that I want my students to have is that if this is 0.8 something standard deviations here, then it's also the same amount of standard deviations here. Because in this side, the standard deviation is 1. So if the point z is 0.8, 0.8 is exactly 0.8 away from 0. And so 0.8 is 0.8 standard deviations because the standard deviation is 1. So this turns out to be the amount of standard deviations that this needs to be away from this in order to have this much probability to the right. So this is going to happen in the orange side as well, where the distance is 2. It's not 0.8 like I found here. The distance is 2 because it's the distance between 5 and 7. But that 2 needs to be 0.8 standard deviations. And in this case, this is not exactly 0.8, it's 2 because the standard deviation is not 1. So we need to figure out how much this is from this very easy equation. And the answer to the problem was 2.38. Now, if you are used to doing this with the formula for the standardized normal variable in the booklet, you should definitely pause the video now and go do it with that method to see if you find the same answer. I hope you do. But one of the reasons why I don't like this formula, and it's by no means the main reason, okay? The main reason is the hiding of information that I was just talking about. But another reason is that when I see students trying to use the formula from the booklet, I see them plugging the numbers from the problem in the wrong variables for some reason, because there's 4 variables in the formula, z, x, mu, and sigma, and they tend to get mixed up. But if you don't mix them up, we have to admit that this is a lot faster as a method to solve this exercise than the thing that I was just doing that includes sketching 2 normal distributions, which I feel is helpful to me because it clarifies what I need to put into the inverse normal in the calculator. If I'm looking at this green one, it makes it easy for me to know exactly what to do with the calculator to find this number. But I don't know, if I can get over that, I feel like it might be faster to solve this problem by just using the formula. So my worry is that, is this thing that I'm suggesting to my student analogous to if I was telling them to complete squares every time instead of using the quadratic formula? Because the quadratic formula is just what the conclusion is going to be from the completion of squares, in much the same way as this formula is the conclusion from the sketches of normal distributions that I was just doing. So I think that I'm making different choices in different moments for different reasons. But what I'm saying is that I'm open to hearing more arguments. And another thing that sometimes students ask me about the formula booklet is if I personally know every single thing in it by heart. That is an extremely fair question, especially considering that during class I don't ever look up something in the booklet. But the answer is no. I don't actually know every single thing in it by heart. There are a couple of things that I have to look up, and I find them very annoying. So let me share one with you. Here is Euler's method, which I don't think should be a formula because I've taught you Euler's method in my previous video, and if you understand what Euler's method is doing, then this is it. You don't need the formula. It's very similar to actually the term of an arithmetic sequence. But anyway, it doesn't bother me that this is here. I just don't think it's necessary. But the integrating factor, that is so annoying because I don't know the stupid integrating factor by heart. I know how to solve differential equations using integrating factor. I know what this is about. I know that it's like a smart application of the product rule, but it just takes me so long to work around that procedure every time I realize that a differential equation is going to require the integrating factor. I wish I knew this one by heart. It would speed up my life. But then again, when I come to this point in the high-level course, that's at the very end of the course, the students have learned so much already that I am fine with just telling them, listen guys, this is one of the most difficult things in the whole syllabus. You've learned so much math over the past 2 years. I know that you are capable of understanding concepts. And we have this big exam right around the corner where this is just a tiny little piece. I'm not sure if I've ever even seen this used in an exam question. So, in those conditions, I feel pretty comfortable telling my students I'm not going to explain to you where this comes from. It's just one of the methods of solving differential equations. When it's this type, just do this and you're done. So if you're a student, let me know, how do you use your formula booklet? Do you know basically where to find the formulas that you need? What are some that you know are there, but you don't really look up because you just know it? How does that usually work for you? Do you sometimes use the formula wrong because you didn't take the time to look it up? Some formulas that you don't understand but would like to? Anything at all about the formula booklet, please let me know.